Good morning. We are going to talk about solving systems of equations by using a method called substitution. Now maybe you've seen this method before in Algebra 1, but I'm going to give you a quick review of how it works and what the solutions mean. So we start off with two linear equations with x and y, no exponents in either of those. And the goal is just to figure out which ordered pair of x and y is going to be a solution to both equations. And as you probably know, one of three things is going to happen. Either there is no x and y that is a solution to both of them. Any solution x, y that is a solution to one of them is not a solution to the other. So that we call that no solution. And that usually means that the lines are parallel, at least in two dimensions. Then we have infinite solutions that could also happen where any x and y that is a solution to the first equation is also a solution to the second equation. And then what more than often happens is that you get one unique solution. So even though each line separately has a bunch of x's and y's that are solutions to that particular line, there is only one x and y that is a solution to both lines, and that is the x and y that we're looking for. The trick to figure out when to use substitution is to look for an equation that has x equals something or y equals something, at least with lines. When we get to more complicated functions, you might want to use substitution a little more often than that, but we'll talk about that when we get there. So look for an equation that has x equals something or y equals something, and that's usually a good indicator that you need to use substitution as opposed to any other method to solve. So let's do an example together. The first equation we're going to have is y equals 2x plus 1, and the second one is 4x plus 3y equals 38. So notice I have a y equals equation here, which is what I'm looking for. So I look at what's on the other side of the equation in the y equals equation, and that's 2x plus 1. So everywhere on the first line, the y coordinate is equal to twice the x coordinate plus 1. Well, I want that to be true for the second equation too. So I'm looking for the y in the second equation, and there it is. So in the second equation, I want that y to also equal 2x plus 1. So what I'm going to do is I'm going to make a substitution. I'm going to replace that y with 2x plus 1. And that's what it's going to look like. And notice what happens. I went from having two equations with two variables to having one equation with one variable, and that I can solve. So I go ahead and solve it. I notice that there's a 3 outside those parentheses, so I'm going to distribute the 3 to the 2x and the 1, making the 2x into a 6x and the 1 into a 3. So now I have 4x plus 6x plus 3 equals 38, and it becomes even more easy to solve. I see the 4x and the 6x on the same side of the equation. That can be simplified to give me 10x. So now 10x plus 3 is 38. If I want all of my x's on one side, then I've accomplished that. But if I want any term that doesn't have an x on the other side, I'm not quite there yet. I have this extra 3 on the left-hand side. So if I subtract 3 from both sides, it will go away on the left-hand side, and the right-hand side will become 3 less than what it was. So I've got 10x equals 35. And now the only step I have left is to divide. Well, 10x divided by 10 is just x, and 35 divided by 10 is 3.5. So x equals 3.5. Hopefully, that's my guess. I may have done something wrong. So what I do with this now is I figured out half of the information. I figured out that x is equal to 3.5. So I go back up to one of the equations, and I'm just going to use the first one because it is in the form y equals something, and I do want to know what y is. So I'm going to replace, again, substitute the x in that equation with 3.5 because that's what I think x is equal to. So I replace x with 3.5, and I get that y is equal to twice that plus 1. And so that's 8. So I think that my solution is 3.5 and 8. Notice that I keep saying I think. What I need to do in order to make sure that I haven't made a mistake is go to the second equation and check to make sure that my solution is correct. So I check with the other equation, and I plug in 3.5 for x, and I plug in 8 for y. And hopefully I will get an equation that is true. So the left-hand side of the equation looks like this. 4 times my x, which is 3.5, plus 3 times my y, which is 8. That becomes 14 plus 24, which is in fact 38. So I now know that my solution is x equals 3.5 and y equals 8. All right, and I've checked it, so I know I've done a good job. All right, let's look at a couple more examples because that one worked out where there was one unique solution, and we know that that doesn't always happen. So I'm going to start out with an equation that says x equals 3y minus 6, and the second equation is 4x minus 12y equals 15. Well, just like before, I've got x equals something, so that means I'm going to use substitution. So what is x equal to? 3y minus 6. That is what I want x to be equal to in the other equation as well. So this x I want to replace with 3y minus 6 because that's what I want it to be equal to. So now my equation looks like this. I've made the substitution, and now I've only got one equation with one variable instead of two equations with two variables. I distribute the 4 outside the parentheses to get 12y minus 24, and then the rest looks the same. Minus 12y equals 15. I notice on the left-hand side that I've got a 12y and a minus 12y, so those go away because 12y minus 12y is nothing. And so all I have on the left side is negative 24, and all I have on the right side is 15. I've lost all of my variables. So I've got an equation that says negative 24 equals 15. Well, when is negative 24 equal to 15? Never. Negative 24 can only equal negative 24, and 15 can only equal 15. So if you get a situation where you have number equals number, but those numbers aren't the same, or they're not even equivalent, then that means you have no solution. There is no x and y on the first line. That's a solution to the first line. That is also a solution to the second line. There's no points where they intersect, so no x's and y's that are solutions to both equations, which means they're parallel in this case. Okay, looking at the second of these two examples, y equals 5x minus 1 and 15x minus 3y equals 3. All right, I have y equals something, y equals 5x minus 1. So in the second equation, I'm going to look for my y. And in the second equation, I also want y to equal 5x minus 1, like it is in the first equation. So I make that substitution, and 15x minus 3 times 5x minus 1 equals 3. So the only thing that changed was y was changed to 5x minus 1. I distribute the negative 3 to the 5x and to the negative 1, and that gives me 15x minus 15x plus 3 equals 3. Again, I've got 15x minus 15x, and if I simplify those, I get nothing, and so I get 3 equals 3. This is a similar but different situation than I had before in that I don't have any x's or y's anymore, I just have a number equals a number. But the difference now is the numbers are in fact equal. So when is 3 equal to 3? All the time. That tells me that I have an infinite number of solutions. So any solution to the first equation is going to be a solution to the second equation. And just for a couple of examples, 0, negative 1, if you try plugging that into the first equation and the second equation, it will work. If I try plugging in 1 for x and 4 for y, that will work in both equations. And if I have 2 points that are solutions to both equations, and it only takes 2 points to make a line, then I know that those two lines, y equals 5x minus 1 and 15x minus 3y equals 3, those two lines are the same line. So every point on one line has to be a point on the other line. So those are examples of the 3 things that can happen when you try and solve a system of equations by substitution. We'll do more practice of this tomorrow. If you have any questions, let me know. Otherwise, I will see you tomorrow.